You're a mountain biker at the top of a ridge. Somewhere below is a valley, the lowest point in the landscape. That valley is your answer, the parameter values that best fit your data. But you can't see the whole terrain. You can only feel the slope under your wheels. How do you find the bottom? Every optimization method is a different riding strategy. Welcome to the mountain biker. The simplest strategy, always ride downhill. At each position, feel the slope, that's a gradient. Point your bike in the steepest downhill direction and pedal. Take a step. Feel the slope again, adjust direction and pedal again. Repeat until the ground is flat, you've reached the bottom. Gradient descent is the foundation of all optimization. Train a neural network. Gradient descent. Fit a regression model. Gradient descent. Minimize any differentiable loss function. Gradient descent. How far do you ride between slope checks? That's the learning rate, your gear selection. Too high a gear, you blast past the valley and end up on the opposite ridge. The loss oscillates wildly. Too low a gear, you barely move. It takes 10,000 steps to reach the bottom. The right gear, smooth descent, reaching the valley in a reasonable number of steps. In practice, adaptive methods like Adam adjust the learning rate automatically, higher gears on flat terrain, lower gears near the valley floor. The valley floor is the maximum likelihood estimate. Maximum likelihood asks, what parameter values make my observed data most probable? The loss function is the negative log likelihood. Minimizing it is the same as maximizing the probability of the data. For a normal distribution, ML gives you the sample mean and variance. For logistic regression, ML gives you the coefficients. The valley is always defined by your data and your model. You don't know where to start. Grid search checks every trail intersection on a systematic grid. Thorough that's load in 10 dimensions, a grid of 10 points per dimension means 10 billion intersections. Random search picks random starting points. It sounds wasteful, but in high dimensions it's surprisingly effective. Each random point samples a unique value in every dimension, while grid points redundantly repeat values. Bergster and Benju show that random search finds good hyperparameters faster than grid search for most machine learning models. 4 strategies for finding the valley. Gradient descent follows the slope. Learning rate controls the step size. ML defines what valley means for your data. Grid and random search handle the cold start. But what if the valley you found isn't the deepest one?